It's really good to be here this morning, and I'm excited to get to talk to you some about the Rust project and some of the work that we're doing there. I gotta say, it's a little bit surreal being here. So I work at Microsoft, and if you told me back when I started my career that someday I would be presenting as a Microsoft employee at a Linux conference about work that we're doing at open source, I would have been a little bit surprised to believe that. But I'm really glad to be here, and I'm glad to get to talk on behalf of the Rust Leadership Council and the Rust Project and share a bit about what we are doing in the Rust Project. So to tell you a little bit about what, I've been involved with Rust for a while. So currently I'm working at Microsoft as a software engineer in DevDiv, and mainly this is an internal focus thing now. We are at Microsoft starting to use Rust a lot internally. And so that means that we need a team to support and make sure that we can meet our requirements and be successful in shipping Rust code. But part of that is also making sure that we have a healthy upstream Rust project, making sure that it's well-staffed and well-supported. And so I get the privilege of spending a lot of time working in the open source community. So I do a lot of different things within the project, but the thing that's maybe most relevant for us today is that I'm the representative for the Rust compiler team on the Rust Leadership Council. And I'll explain a little bit more of what's involved with that later on in the talk. But my history with Rust really goes back pretty far. When I was in graduate school, I had the chance to be an intern. I think one of the first interns on the Rust project at Mozilla. So this was kind of 2011, 2012, when Rust was really new and exciting, and just lots of changes happening very quickly. And so that means that I also get to share a lot of kind of my personal history, or when I talk about the history of Rust, I get to share my own experiences in that too. So I'm excited to be able to do that. I was thinking about what I wanted to present today, so I took a look at the Ubuntu Summit website, and this paragraph that I have up there is, I think, kind of maybe the theme for the talk, why we're here. And there were two phrases out of this that really stood out to me. The first one was that we were looking for people who are not satisfied with the status quo, who really would like to see better and more reliable software. And then the second is this idea of doing excellent engineering in the open. And both of these, I think, really resonate as a Rust contributor, as a Rustation, because Rust is really about challenging the status quo, about saying, hey, with better tools, with better programming languages, that can form a foundation for better and more reliable software. And Rust has been open from the very beginning. We care a lot about doing excellent, high-quality engineering and doing that in the open. And so I thought this was a great idea to talk about these two things. So these are going to be kind of my themes for the talk, and I hope they come through as we talk about it. But looking at the ways that Rust challenges the status quo and tries to build better software, better systems and things like that. And then looking at the way that Rust strives for open, excellent engineering and doing that in the open, having a collaborative, welcoming process for the community. So for the rest of the talk, I have kind of three sections. We'll have a brief intro to Rust, because I imagine there are, some people use it, some people don't. So, kind of set a baseline for that. I want to talk some of the history of Rust and how it got started, how it got to where it is today, and some of the things that we've learned in that process. And then, once we've done the history and we've caught up to today, I want to talk about how the Rust project runs today and the ways we continue to evolve the language and develop it and do this excellent engineering in the open and build, make the language even better than it is today. So one thing I want to just kind of acknowledge, how many of you have had the opportunity to run into the Rust evangelism strike force on the internet before? Yeah, so in the Rust community, we're really known for being sometimes perhaps overzealous and promoting the good news of Rust. I'm not here to convert you to Rust. I think Rust is an amazing programming language, but there's other good languages out there too. And that's okay. You should pick the language that works best for you, that you're most comfortable with. If that's Rust, great. But what I really want to focus on instead is inspiring better software and share some of the things that have worked for Rust. I'd really like this to be a talk about, even if you never write any Rust code, there's something you can take away from it that you can learn. The goal is to get better software, better technology that we all work with. And if Rust is a tool that does that, then great. And then I feel like I'm here a bit as a guest of the Ubuntu community. And so I'd like to have this chance to learn from you as well. One of the things that Rust does is we try to learn from other communities and take things that have worked well and adopt those and share the things that work well for us. And so I hope this is a chance for me to learn as well and have new ideas to bring back to the Rust community. So with that, let's get into our introduction to Rust. If I were to give Rust maybe a one-sentence summary, I would say it's a safe systems programming language that's suitable for the kinds of programs that you would have previously written in C++. So this means it's a language that gives you a lot of low-level access and low-level control to the machine, the way your data is laid out and things like that. But it has a lot of other sort of features built on top of that. It has a very powerful type system and a really flexible trait system. Probably the thing it's best known for is its borrow checker, and that's a way of it's a sort of safety system on top of pointers and references that allow you to do things that can be really aggressive and performant, but you can do it with the confidence that the compiler is making sure that you're avoiding the kinds of errors that can be tricky to fall into with complicated memory access patterns. Like I said, the language is ahead of time compiled, and so this means it compiles down to native machine code and can run very efficiently. And part of that is also that the language has really minimal runtime requirements. I should probably just say it has no runtime. You can compile Rust to run on bare metal. You can write the operating system in Rust, and so you don't actually depend on having services provided by the operating system there. Anyway, one slide's not really enough to show all the features of Rust, but those are a couple of highlights that I wanted to share. One of the things that I think is particularly special to Rust is the way that it's built around this idea of ownership. And so I wanted to have just a short program here to explain, or to maybe demonstrate a flavor of what that looks like. So in line one, I've created a new structure called thing struct. I've defined two functions, consume thing and borrow thing. The really maybe relevant difference there is that ampersand in front of thing and borrow thing. So that's saying we're taking this by reference, or in Rust we sometimes call them a borrowed reference, whereas the first function, consume thing, takes the value by ownership. And if you know Rust, you're probably already kind of looking at this and thinking, hey, this might not work. And this particular program doesn't. But this highlights what Rust is doing with ownership transfers and movement and borrowing. So in this main function here, when I create a thing and then I pass it to consume thing, that passes by value, or sometimes I like to say it passes by move. You can think of it as moving it from the caller to the callee. You're giving up ownership of it in the caller and transferring that to the callee, and then it's up to the callee to take control of that and to take care of cleaning it up when it's ready or handing it off to someone else. That means that from the compiler's perspective, after we call that function, this t variable has been deinitialized. It's now uninitialized memory. And so when we try to borrow it, we pass a reference to it that the compiler is complaining there that this thing has been moved and you're trying to borrow it, and that's not okay. And this is an example of the kinds of things that Rust does to help you avoid errors with uninitialized memory or things that have been deinitialized or things like that. So that was our introduction to Rust, and now I'd like to share a bit of the history of Rust, how we got to where we are. I want to start off with this, what I've called the legend of Great and Whore in the elevator. This is somewhat rooted in truth, but I think at this point I'm calling it a legend because I'm kind of going to embellish the details a bit to make the point I want to make a little bit better, or to tell the story in a little more entertaining way. So the legend goes that one time, a long time ago, Graydon was, he was living in his apartment on like the 14th floor of this building, and he was, coming home from a busy day and was tired and just looking forward to relaxing in his apartment. When he went to go push call the elevator and get up to his apartment, it was, I guess, a fancy elevator with like kind of a screen on it and all that, and he was greeted with the blue screen of death. on there. So the elevator control software had crashed. The elevator was inoperable, and so Graydon had to take the stairs all the way up 14 flights of stairs to get to his apartment. As you can imagine, it gives you a lot of time to think when you're climbing up all those stairs. And Graydon was reflecting on the state of software and how so much of it is unreliable, and we really ought to be able to do better. To put a point on it, we struggle to even make elevators work, and that's not really, we'd like to do better than that. And then Graydon got the idea that maybe if we had a better programming language, we could do that. And so starting off on Rust was really this idea of let's find things that have worked well in existing programs. If you've written C++ for a long time, you have a good idea of the kinds of patterns that lead to robust and correct code. So why don't we try and codify those in the language and let the language help you follow those? So Graydon got up to his apartment and started working on a new programming language. And ultimately, what that led to is what we have today as Rust. Here's kind of a timeline of the Rust project. So Graydon started working on Rust back in 2006. And for a couple of years, it was really just a hobby project that he was doing on his own time. But then around 2010, he shared it at Mozilla, where he was working. And Mozilla thought, hey, this is pretty cool. Let's put some more effort into it. Let's build a team. Let's keep experimenting with it. Around this time also, so we had an excellent talk yesterday about Servo. This is also when the Servo project gets started. And that's something that I think is particularly cool, this relationship between Servo and Rust, because from Rust's perspective, it gave this application to sort of co-develop the language with. And I think for a lot of times when you have a really successful programming language, there's usually some killer app that was developed alongside it. The one that kind of immediately comes to mind is C and Unix, where the C programming language was essentially developed so that they could write Unix. So C allowed people to write Unix, and then Unix sort of relies on C. C is the language really of Unix. So that synergy there, that collaboration, and Rust had a lot of that with Servo as well. Being able to have an application that's not the compiler. Rust is a self-hosted compiler, so the compiler is written in Rust, but also having another project to really guide and inform the language decisions is really nice. In 2012, we had our first public preview release of Rust. It was Rust 0.1, and that was a point to say, hey, we're ready to let people start experimenting with it. The language was still very experimental. There was a lot of churn in it, but people started to try it out, and we got a lot of great feedback from it. A few years later, in 2015, we released Rust 1.0, and the theme of that was really about stability. It was about not having to do these breaking changes all the time, having to just constantly update your code to keep up with the changes in the compiler. And then since then, we've continued to develop the language through this mechanism of additions, which are ways to sort of make changes that allow the language to evolve further. And I'll get into more of that in the talk to come. And I'm excited that our Rust 2024 edition is coming out soon. We're hard at work on that now. It's actually going to come out in January of 2025, but we'll finish the edition in 2024. But because of the sort of train model, it'll be 2025 before it's unstable. So when Graydon first started sharing this project at Mozilla, he gave a talk that there's a link there if you want to go find the full talk. It's pretty interesting as a bit of language history. But he had this slide in there that talked about how this has been kind of a young and immature project, but that the design's mostly done. We've got 90% of the language features working and around 70% of the runtime. So essentially just a little bit more work and the language will be done. We know with hindsight now that it was actually 5 more years before the language was finished, or before we got 1.0. And that was because as we worked on it, there was a lot of churn that went through it and a lot of evolution and iteration on the language. The easiest way to see this is to look at all of the release notes that we had. So in 0.1, we had this. We ended the release notes saying future code will break unexpectedly. I don't know that it really was unexpected that there would be breakage, but the particular breakage was maybe hard to predict. And then if we look at the release notes coming up after that, each one has this long list of, most of those bullet points there are syntax changes that were made to the language. And most of those would mean if you are writing Rust code, you'd have to go and update your syntax to work with the new compiler. So, this works for some people with that want to, keep up with the changes in the language, but at some point you kind of just want to write code and have it be done and have it keep working. So that was the goal when we moved towards stabilization. To give you an idea of how the language has changed, though, up here I have an example of code from Rust as it was in about 2010, and then what an equivalent program would look like in modern Rust. I put 2024, but I think the same program would work in 2015 in Rust 1.0. When I use a slide, I update the date on it to show that it still works now. So, structurally it looks a lot the same. The curly braces are in essentially the same place. But you can see some changes, like, early Rust had this idea of objects. It was kind of a prototype object model, and then that was replaced with struct and impl. So we made this clean separation between describing the data structures that you have and then attaching behavior to those data structures, either in the form of inherent methods like this, or by implementing traits, which are a way to sort of package, essentially like interfaces, a way to package up a set of behavior and then say this is how this particular type implements that behavior. And then you can kind of see small syntax changes, like, instead of auto for declaring variables, we use let, and logging had special syntax before, and then it was replaced with a macro, this println macro, and so on. But that gives you a flavor of how the language has evolved over the years. But then, as I mentioned, we released Rust 1.0, and this was really about stability for the language, getting to a point where you could rely on your Rust code still working, so you don't have to just every time there's a new Rust release rewrite your code. It's great for if you have hobby projects where you work on it and then come back to it 3 months later. Your program would still work after this, where that wasn't really true beforehand. This was great. It was a time, the core ideas of the language were done, and we were ready to commit to them and support them in the long haul. And then really the flavor and the approach that the project took towards evolving the language changed a lot at that time. I'd like to take a minute to talk about some design principles behind Rust. And some of these were there from the very beginning. They, kind of built in from the beginning to the Rust ethos. But some of these were either refined or sort of grew organically through the course of this early development in Rust. And so I'd like to share some of the principles that stand out to me. Here's my list, and this is my list. If other people were giving this talk, they might have slightly different things on here, but I think all of these things are things that we generally agree are valuable in the way that we design and develop Rust. So I'll go into each of these a little bit more detail now. And the first is this idea of being safe and sound, and that's that your program behaves as specified, the behavior is well-defined, you don't have things like out-of-bound memory accesses. We have array bounds checking built into it. We rely on things like the borrow checker to prevent things like use after freeze and double freeze and all kinds of things like that. Some of the features that really build into that are obviously memory safety, but then again, if you're working in low-level hardware, a lot of times you need to escape that, and so we have this unsafe mechanism that lets you basically encapsulate these things where you have to do things that the Rust compiler can't understand and verify as safe. But if you encapsulate that inside a safe API, then you can use it outside of that boundary with confidence and without having to worry about memory safety errors there. Type soundness is also an important part of this. And so, broadly I would say type soundness is that if your variable is declared as an integer, it holds an integer, that things hold the type that they say that they do. And then that avoids a lot of errors with like type confusion and where you think you have one thing, but it was this other thing because it was illegally casted or something like that. And then part of memory management is automatic cleanup. So Rust has this drop trait which works a lot like destructors in C++. And so when the compiler can see that a variable is no longer needed or a value is no longer used, it can clean it up and free the memory with it. And so that helps prevent things like memory leaks. And because this is automatically done by the compiler, it also prevents some of the issues that come from when you try to do it yourself and maybe miss a detail or a corner case on it. The next principle is this idea that if your code compiles, it works. Obviously, this is kind of an ideal we aspire to, but you know, a talented program can write bugs in any language, and that's true of Rust too. You can write buggy Rust code. But Rust really strives to provide tools that will make it easy to make sure your program is correct by construction and works the way that you expect. So there are a lot of language features that encourage correct programs. One example of that is the match construct, where you can sort of consider different cases, different categories of things that could happen, and then the compiler can check and make sure that you've covered all of those things. And so you don't have this case where, oh, I forgot to handle, you know, I have an error case here and I forgot to handle it. The compiler makes sure you do that. And then that's also supported with this rich data type language. I mentioned struct and enum. There's a lot more to it. Enum is particularly nice. It lets you have a type that can be, you know, this thing or this thing or this thing with different data attached to that. And that is nice because sometimes you have, you know, the state of your object evolves through time, and sometimes it's hard to tell, like, is this field valid now or not? And with enums, it's nice because the invalid fields just don't exist when you're in that state. So that, coupled with match, helps you be really robust in reasoning about the state of your program and what kinds of things can happen. The next principle is this idea that if it works, it keeps working. And that's really another way of saying our stability guarantee. You know, you don't want to have to rewrite your code every time you upgrade the Rust compiler. And so we work really hard to make sure that we don't break backwards compatibility as much as we can avoid it. There always are cases where we have to do it in a very limited way, but as a principle, we're very cautious about making those kinds of changes. But of course, we still want to evolve the language. Rust, even modern Rust, looks a lot different than 2015 Rust, and that's because we have this ability to evolve it. So how do we do this? Well, there's a few things that we do that we use to make this happen. The first thing is this release train model. And I think Rust really borrowed this from the browsers. That makes sense coming out of Mozilla, where Firefox was shipping on a 6 weeks time schedule, and Rust follows that same model now. So as an example, we just recently, a couple weeks ago, released Rust 1.82. That means we now have Rust 1.83 in beta, and then we have 1.84 is the current nightly release. Most of the development happens in the nightly branch, and then every 6 weeks we promote that. We sort of move the trains along and promote to the next stage on there. We do have the option of doing backports into the beta branch before we release it to stable. But my sense is these are pretty uncommon. Well, maybe a handful of patches that we have to do each release, like 3 to 5, something like that. Almost all of the development happens on nightly. We also have this tool called Crater, which is really cool. It goes and it can pull every Rust crate that's listed in crates.io, many of the ones that are on GitHub too, libraries or projects that are written in Rust. And it goes and fetches all of those and compiles those with a new compiler and reports anything that has changed, anything that breaks that didn't break before. And this gives us this really powerful ability to assess the ecosystem impact when we're making changes that might be breaking. Sometimes it'll say, hey, someone could be depending on this, but we think it's unlikely, so let's see, does anyone actually depend on that behavior? And we can say, oh, okay, we found 3 crates out of 50,000 of them that would be impacted by this. And so this is really helpful to be able to tell what's happening with Rust, what people are using, and can help us detect unexpected breakages also. So there's sometimes we make a change where we're like, oh yeah, that'll be fine, and then we realize, no, it actually has this surprising impact over here, and then we can use that to reconsider whether we want to make the change or not. We also have feature flags. So, you can't implement a lot of the language features that we're trying to add in 6 weeks. So we need some way to allow them to evolve over multiple releases. And we do that through feature flags. So we can design a feature behind a flag. This is only available on nightly, and that's because if we put it on stable, people would just start putting the feature flags in their code, and then we'd end up having to support it. We want to explicitly not make a backwards compatibility promise on something that needs an unstable feature flag like this. But we still want people who want to experiment with it and take on that risk to be able to play with it and try it out. So one example, a feature we're working on now is generator blocks. So you can enable that by adding this gen blocks annotation here. And that lets you write functions like this. So we can write gen fn, count to 3, we yield 1, yield 2, yield 3. A nice simple way to count to 3. This is familiar if you're in languages like Python or JavaScript, or many languages have generators, and I'm looking forward to seeing them in Rust as well. And then we also have our stabilization process. So we've done this development behind a feature flag, and then at some point we want to turn it on by default and make it an official part of the language. This is by necessity a conservative process. Because if we make bad decisions, we're kind of stuck with them because we have this backwards compatibility promise. So the solution there is to only make good decisions, right? That's not too hard, but it means we have to be really cautious, and that's in a lot of cases the main reason why development in Rust can sometimes feel really slow. So we want to make sure that we're confident in the design, we've had the chance to experiment with it, it's had time to bake, and that we're willing to support it indefinitely. So once we get to that point where we're ready to do that, we can leverage that feature flag mechanism to turn the feature on by default, and then it becomes part of stable Rust. We also have this mechanism for additions, which we talked about before, which is really a way of unblocking or unlocking language evolution. So there are some times where we, want to make a change, but because of the way something worked before, we need to change the existing behavior as well. And additions give us a very controlled way to be able to do that. So additions are opt-in. When you write your Rust project, you define what addition you're using, and then you can interoperate. So you can have a Rust 2018 crate link with a Rust 2021 crate, and vice versa. But then within your crate, there's Rust is using the rules for the edition that you've chosen. And so that makes it so you can have this controlled choice to move from an older edition to a newer edition. That will mean making changes to fix your code. But in many cases, we can automate those as well. We have a tool called Cargo Fix that can basically just go through and mechanically change your code so that you have the old behavior if that's what you wanted. As you can see from some of the changes that we've had, this is, I think largely additions are about unlocking future work. And so it's not so much, for example, in Rust 2018, we reserved async and await as keywords. We did not actually add Rust or add async and await like the features in Rust 2018. That came a couple of releases later. But by reserving these keywords, that gave us the freedom and the flexibility to do that without breaking existing code, at least once you've migrated to 2018. And with Rust 2024, I think a lot of the changes that are going in there are kind of a similar flavor. There are changes we'd like to be able to make, but we need to make these opt-in changes in behavior first. So our fourth principle that I want to talk about is this idea of building great tools. There's a list I have up there of some of the tools that we develop as part of the Rust project. So the compiler itself, we have Rust Format, Rust Analyzer, which is this really, I think, excellent IDE tool for looking up definitions of your code and applying fixes and just kind of understanding how your code works. And there's Cargo, which is the Rust build system, and does a few other things as well. And then also this idea of having built-in testing. I like a lot. I think when I write Rust code, I test it better than code that I write in other languages, and a lot of that is because you just have in the default setup for the language, you can just add your test in there. You run cargo tests, they all run. It's really seamless to do that. I also want to highlight Rust Format, and because I think it's kind of interesting that this got really mature really early on in the process of Rust, and I've always thought of an auto formatter as being something that would come later in the language evolution. But this ended up being extremely valuable when we were making syntax changes for the Rust compiler, or like in the Rust language, because the Rust compiler is written in Rust. So when we change the syntax, we also have to go rewrite the Rust compiler to use the new syntax. And Rust format ended up being really valuable for that because we could have Rust format read the old syntax and then reformat it using the new syntax, which made it much more seamless to update our code and adopt language changes in a compiler that is itself written in this changing language. Part of this excellent tooling idea is to have helpful error messages. We saw an example of that earlier, of the kinds of error messages that Rust gives. And I like this quote a lot here from Esteban Couver, who has really driven a lot of the work around diagnostics and error reporting in Rust. So he says the primary function of a compiler is to take malformed code and emit diagnostics to help the programmer turn it into well-formed code. A compiler is an error reporting tool with a code generation side gig. And I really like that because we a lot of times think the compiler is about generating your code and making your code run. But this kind of turns that around, and we can think of it as the compiler is really helping you write code that's correct. And then, that's why a lot of your work is this dialogue with the compiler. I tried something, and it says, no, I don't like that. Here's the change you should make. So you make the change, and you fix it. And then eventually, it's, almost anticlimactic that it's like now it can generate code, and your code works the way you expected it. And that's because of our helpful error messages. And then our fifth principle, and our last one, is this idea of learning from others. So the Rust reference has this page in it that I like a lot, which says that Rust isn't a particularly original language. And what we mean by that is that almost every single feature that's in Rust is we've taken from some other language. We got inspired by some other language. I think really, if anything is novel about Rust, it's this particular combination and making these features work well together. But yeah, just all of the features that Rust has, we've borrowed from other languages. It's great to be able to take good ideas that have worked elsewhere and find a way to make them work within Rust as well. Okay. So that's our history of Rust and introduction to Rust. I want to spend some more time now talking about how we build Rust. The first thing I want to talk about is the way that Rust is structured, the Rust organizations are structured. And I want to talk about the Rust Foundation and the Rust project. These are two distinct entities, which I think is maybe a little bit uncommon. So we have the Rust Foundation and the Rust project that work well together, but they actually have different responsibilities. And so it can be easy to conflate these, but they are different. The foundation's really there in support of the project. So let's get into a little bit more about what that looks like. First of all, the Rust Foundation. Its primary goal is to support and promote the Rust project. So to support us on the project side, to develop the Rust language and really make a great programming language. So that means a few things. That means this idea of being a steward for Rust. It also provides legal services for the Rust project. So there are some times where we need a legal entity to sign a document or to own intellectual property or things like that. And that falls within the foundation's role. They look over the things like trademarks for the Rust programming language and provide this legal entity there. And then a lot of the work they do is around fundraising, and that primarily comes through corporate memberships. And then taking these funds, they can then deploy that in service of the Rust project and to enable the Rust project to do excellent work. The foundation has several components within it. The first one I want to talk about is the board of directors. And so these are the people that oversee the foundation and set the strategy for how the foundation works, what things they should be pursuing. One of the things that I think is somewhat uncommon about the way this is set up for Rust is that the half of the voting power within the board of directors is reserved for the project. So the project appoints what are called project directors, and then the member companies in the foundation appoint member directors, and then that makes up together the board of directors, and then those two halves have equal voting power. And so this gives the project a lot of say in the strategy and the direction that's set by the foundation too, which helps us really focus on making Rust great. I mentioned the Rust Foundation it's a foundation made up of different member companies, and so they play a part of this. They're a stakeholder in the foundation. And then we also have the foundation staff who manage kind of the day-to-day operations of the foundation. And actually, some of the staff work on the Rust project itself in engineering roles or other support roles like that. Okay. So now let's shift gears and look at the Rust project instead. This is the entity that really does most of the development on the Rust programming language and then most of the engineering that goes into Rust-C and all of its related tools and things like that. It's largely a volunteer organization, so people come and help out either as hobbyists or, some are sponsored or hired directly to work on it. And many of us are, in a situation like myself where we work for another corporation, and part of our work for that is to work externally or upstream on the Rust project. But it's largely volunteers, mostly people that are not actually hired by the foundation or the project itself to work on it. The project itself has several components in it. So I'll go kind of right to left on there. We have working groups, which are these entities that are either geared towards working on a particular aspect. So in examples, we have the async working group that works on designing and developing, building out Rust async feature set. Some of them are more almost kind of like special interest groups. So we have like embedded or game dev, which are people that are interested in using Rust in those domains. And they may maintain a set of crates to help make that work better or provide resources if you're wanting to work in these domains as well. The bulk of the project, though, is this set of project teams. These are top-level teams, and they're the ones that have maintainership responsibilities over different aspects of Rust. So, for example, the language or the compiler and things like that. And then we have the leadership council, which is made up of representatives from each of the top-level project teams. So here's our set of, at the moment we have 7 project teams, these top-level teams. This changes over time, but I think we have a pretty good set right now. So there's compiler, the library teams, moderation, dev tools, infrastructure runs things like our CI, and some of the different tools we use to communicate with each other. There's the language team that owns what the Rust language itself is, and then Launchingpad is kind of this umbrella organization for all of the working groups so that they also can get representation within the project. These teams can be further subdivided into sub-teams. So for example, the language team uses this to great effect. We have things like the Lang advisor. We have a team focused on documentation, the style guide, having a spec, operational semantics. It's not listed on there, but there's also a types team that is kind of a dual sub-team of Lang and compiler. And so that lets the Lang team delegate authority and responsibility for these subparts of the language as well. And that can help increase our bandwidth and abilities to get things done. And then as I mentioned, the top-level teams can also send, they select members to go serve as part of the leadership council. So that makes the council a little bit different. Most of the teams are sort of, they select their own membership. They invite someone to go join the Rust, or that team and participate in maintainer responsibilities. The leadership council is more of like a representative body, so it's made up of the teams and the people that they send, and then that lets if the teams are not happy, for example, with the way that the leadership council is running, they can change the makeup of that and try to put people on the council that reflect what they want and set a good direction for the Rust project. So the Leadership Council was established by this RFC that basically it was set up to say that the Rust project members confer the authority to ensure successful operation of the project. So there's a few things that the Leadership Council does. Some of that is sort of dealing with cross-cutting concerns across the language or helping teams work together better and facilitate communications, making sure we have the right mechanisms for that. The Leadership Council ends up being kind of the point of contact between the project and the foundation. So we on the council talk a lot with the foundation and work closely with them. And I think in a lot of ways the role of the council is to basically speak as the voice of the Rust project. So sometimes we need to know what does the project want to do or think or say about that. And so for those kinds of statements, that's usually where the Leadership Council comes in and has the responsibility for making those statements and really doing it in a way that actually accurately represents what the project is doing or what the project wants. Okay. So I'm going to spend some more time now talking about how kind of day-to-day life works within the project and the way things get done. There's three things I want to talk about here. One is this request for comment process. And that's kind of how we make decisions at a high level for the project. And then a lot of teams will establish their own process for things that are more local to their domain. So I'll highlight a few of those. And then I want to talk about project goals, which are a new experiment we're trying that I think has gone pretty well so far. So I'll talk about that as this way we have of setting the direction for the Rust project. So first, let's talk about RFCs. RFCs are for big or impactful changes to the Rust programming language. These are things that tend to span several teams and really set a big direction for the project. Most of the time, those are technical. And so some examples of technical RFCs there are things like adding async and await, adding where clauses, changing the way that crates.io works, or things like that. A lot of especially big major changes to the language are done through an RFC, and then that's discussed and approved and so on. But then a lot of the RFCs are also used to shape the way that the Rust project runs. Maybe kind of the most meta thing about that is that the RFC process itself was established by an RFC. I think it's funny that was actually RFC number 2. So somehow we got RFC number 1 without having an RFC process. But yeah. So the RFC process was defined by an RFC, but then we've had other ones as well, like creating new teams, establishing the leadership council, like we talked about, changing the way the Rust release project works, or release process works, deciding we should have a specification, or declaring that we intend to make a Rust 2024 edition. And these are the kinds of process RFCs that we might have. Okay. So I want to talk a bit about consensus, because this is something that I think Rust has pushed really far, this idea of making decisions by consensus. So the question really comes down to how do we know when one of these RFCs or other decisions should be accepted? And sometimes the majority vote is not the best outcome, especially if it's a really close vote. That means that there are really significant concerns or perspectives that are brought up that maybe we haven't done the best job of accounting for. And so because of that, Rust tends to go with this consensus model instead of really trying to get everybody on board with the decision and really putting in the hard work to make sure we can get a decision that everyone wants to go along with. We do this through this process called a final comment period, or FCP, and that's to obtain consensus about a decision. So we have a bot that you propose an FCP on an issue. It puts checkboxes for all of the people on the relevant team for it. And then once we have, no one has raised a blocking objection for it, and we have all but at most 2 missing yes votes for it, then we can say, hey, this has been accepted. We've met our consensus requirements, and we can move forward with it. But then after that, we have this we have this period, this final comment period, that's the FCP part of FCP, for 10 days, which is this chance to say, hey, we've made this decision, we publish the fact that we've done that, and we give people a chance to raise other concerns that maybe hadn't been considered. And so we have this last chance to reconsider it, and we can cancel the FCP if someone raises something that we felt like needed more time to address, for example. But then if we don't have that, then we move on and we accept the decision, we move forward with it, and get to work on it. Okay. I mentioned that some teams have kind of smaller versions of these same processes, and a lot of times that's because RFCs are kind of a heavyweight way of doing things, and for many decisions, you don't need that whole process to do it. So 2 examples of those are MCPs, or major change proposals, and then ACPs, or API change proposals. MCPs are used by the compiler team. They mostly deal with things around the internal architecture of the compiler. So these are, maybe something like compiler flags or something like that. These tend not to have this broad user-facing impact as far as like the syntax or the semantics of the language, but they address how the compiler is developed internally. And so because of that, we can do this decision as a local to the compiler team decision. And then ACPs are this process that's run by the library API team. And that's a way of making changes to the standard library. So for example, proposing a new function or method or trait that's added to it as a new API. And then getting consensus around that and stabilization on that. Okay. So the last thing I want to talk about in this section is project goals. So these are relatively new, but they're really looking at this: how do we set long-term direction for the project, and in a way that is actionable, we can make progress on it, in a way that we can also signal that there's buy-in on it. So project goals are an agreement between an owner and then the Rust teams who support the work. So the owner of a goal is responsible for either doing the work themselves or sort of driving it forward. A lot of times they work with a team of people who are working on this area, but they're the ones that are responsible, like point of contact for how are things going on that and making sure progress is being made. But then there's also Rust teams who support the work. And then that support can look several different ways. One is just kind of a commitment to say, like, yes, this is work that we think is worthwhile, and so if you do this work, we will work with you to get it accepted, because we don't want this case to come up where somebody goes off and does a ton of work, and then the team is like, no way, we don't want this. Why did you waste all that time? So this gives us a way up ahead of time to say, this is a problem we think is worth looking at and worth solving. Other ways that support can come up is things like promising to do code review and allocating resources for code review, or allocating design meetings and getting the teams to make sure to give time or spend time looking at and addressing questions and concerns that are proposed by the project goal owner. So project goals begin with a submission period. So we put out this blog post that says, hey, if you've got a project goal you'd like to propose, here's how to do it. Put it forward to consideration. And then out of that, we come up with a set of goals that we want to accept. This last time, so we started this last May, and we picked 26 goals for the project, and we identified 3 of them as flagship goals. So those were around making the Rust 2024 edition, bringing async Rust and synchronous Rust closer together. So some people describe async Rust as hard mode for Rust, which Rust can be a difficult language, so making it even harder is a little bit tough. So we want to make them feel less like different languages. And then Rust for Linux is something that's been getting a ton of steam. I think it's probably really relevant to a lot of people here, trying to get Rust in the Linux kernel. And so we want to make sure we can provide support for that effort and provide the things that the kernel needs so that they can run using a stable build of Rust, rather than right now where they depend on quite a few nightly features to make Rust work. So we accepted the goals. People go and start working on them. And then periodically we post updates. So like this one, our September goals update on the Rust project blog, talks about progress that's been made on those and how things are going. And then these goals are set up as a like half a year, 6-month process. They're iterative. So at the end of that 6-month period, we do a new slate of project goals. So there's a few things that can happen. We can say, hey, this goal is complete. That's great. We can unwrap it, or wrap it up and say, hey, we don't need to work on it anymore. People can go work on other things. We can say, hey, we still believe in this, and so we want to keep working on it, so we'll continue the goal. Or we can say, hey, we didn't get it done, but we also want to prioritize other work now instead. And then that creates space to either completing goals or deprioritizing them, create space to bring in new goals and address new priorities. And so I just want to mention that this process of selecting new goals is happening soon. Relatively soon, we should see another blog post with a call for goals. And so if you're interested, this is something you can watch or get involved with and help to shape the direction of Rust for the next 6 months. Okay. So we've talked about a lot this morning. I tried to cover as much about Rust and the Rust project as I could in a fairly short amount of time. It's a lot to take in, but I just want to kind of review. We talked about kind of what Rust is and the what makes the language unique and special. The history of Rust, how we got to where we are today, and what we learned from that, and what we've sort of developed as cultural things and the way the project runs. And then we talked about how the Rust project works today, and the way the project is structured, and makes decisions and things like that. And so I hope all this is helpful, and if you use Rust, that's great. Even if you don't, I hope you can learn from this and take some lessons that maybe can make your own projects more successful. And again, like I said, I want to learn from others as well, and so we can make Rust better too. So thanks a lot. I really appreciate the time to talk to you this morning.
Thank you, Eric. I think it's time for questions. We have 2 mics, one on the left, one on the right. Whoever has questions, don't shy away, and please come and ask questions. There we are. We have the first question.
Thank you very much. You described what sounds like a really thoughtful approach to project and foundation governance.
Thank you.
And of course, every project learns from the lessons of the ones that preceded it. But do you think you've been able to avoid some of the missteps that have they've been quite painful in some communities and significant projects? And do you think that the path ahead is going to be, do you think you'll discover new ones, new problems, or do you think that you've solved some problems that have plagued such projects?
I think the answer is probably yes to all of the above on that. Rust itself we've had some really painful things happen in the community too. So, I think like many large projects, problems come up in that. We've learned a lot from that in the past. That's why we have the leadership council now instead of what we used to have, which was the core team, which had similar responsibilities but was structured quite a bit differently. The leadership council is really an experiment. So far, I'm happy to see the way it's going. We haven't seen the real public kind of challenges that the Rust project had a lot beforehand with it yet. I hope it continues that way, but time will tell. It is something we're very aware of and trying very hard to make a project where people can feel heard and that we can address these concerns so that they don't boil up to the extent that they can or that they have in the Rust project in the past or other communities and so on.
Do we have other questions? If not, I do have one as well, but I see someone coming. 2 people, actually.
I'm interested in Crater. So it feels like that would give you a big fire hose of feedback data.
Yeah.
How do you decide if the change, if 0 things break, obviously everything is okay, but if 1 thing breaks, if 10 things break, if 100 things, how do you decide was it an acceptable change? How do you take action upon all that massive data that you must be getting all the time?
Yeah, I'll be honest, I think this is a place where we could probably codify that a little bit better. I think the way it works now is it's largely an input to the teams that are making a decision. We'd like to make this change, here's what Crater said. We've actually seen even different teams within the project have different thresholds for maybe allowable breakage. I know the Lang team, for example, is very, very cautious, and if they see 10 crates that have a problem with it, they're like, oh, I don't know, maybe how much is this change really worth? And other teams can be maybe a little bit more, willing to accept changes like that. One of the things we will do is if it is a small number of crates that are broken, we'll actually go out and send them a PR to say, hey, we would like to make this change. This fixes the problem that it will cause for you. So yeah, I think the best way to think of it is it's an input, and then we sort of weigh against, so that adds a cost to making a change. We like to keep that as low as possible, but if it's a really high value change, we might be willing to accept a little bit more.
Okay, thank you.
Yeah.
We have time for one last question before the group photo. There we are.
Okay.
Thank you. Just going off of your slides, but it struck me that in terms of inside the Rust project, there's tens of teams. In my understanding, there's kind of a fixed cost overhead of contention between teams and organization, generally speaking. Mm-hmm. Just curious what informs that number of teams or sub-teams that are within the Rust project? Is it a function of the number of developers in the project or something else or a combination of things?
Yeah, that's a good question. I think a lot of the teams maybe were developed kind of organically, especially the sub-teams. It's like, hey, we've recognized this area that kind of is separable in some sense that we can we don't need necessarily a high bandwidth communication there, and so we can just delegate a lot of that to the sub-team. A lot of the top level teams in particular, we try to have them have fairly broad authority. They do need to talk to each other a lot. I think particularly around compiler and lang and libs, because all of those, the lang team defines the core semantics of the language. The library team defines the standard library, which has a whole lot to do with how the language feels to work with. And so there's a lot of back and forth that needs to happen there. And then the compiler has to implement support for this too. And so, those teams end up having to have a lot of communication between them. Sometimes the way that happens is you have people that are members of both teams. And so they're attending both meetings, and they can provide this high bandwidth link between the two of them. And then now that we have this representative leadership council, that adds another consideration in there, which is, the larger the council gets, the harder it is to make decisions and get consensus there. And so that adds this pressure to have a smaller number of top-level teams. So when the council started, we had 9 top-level teams, and we've merged some of those teams together, which now means we have 7. And I think that lets the council run a lot more effectively or efficiently.
Thank you, Eric.
Thanks.